So I'm Anmol Zehrah. I am an AI engineer at Atomic Computing. So basic, so I basically work on different AI and ML domain use cases, leveraging the AWS services. So I graduated from Fast Newsys Karachi in June 2024, and my own final year project was basically about computer vision and generative AI in agriculture. And it turned into a startup, and now it is a small startup which is incubated in NIC as well, called Agrotech Vision. And our project got featured in many national and international events as well. Other than that, I also have a research publication and an IEEE conference of ICTAS 2023, which happened in Bahrain. And the topic of my research publication was comparative analysis of different deep learning models. So without further ado, I think we should start with our topic. Okay, so I am very happy to welcome you all to this session, which is titled as Vision Transformers versus CNN, Evolution or Revolution. So, in the next few minutes, we'll basically take a very deep dive into like two of the most powerful deep learning architectures that we have, which are basically now. And they have been powering, like face recognition on your phones, to also enabling, real-time object detection and vehicles and whatnot. And similarly, in the recent years, a new contender emerged, and that contender came from the world of natural language processing. So that basically leveraged the transformer architecture, and because it is using images, so it came out as vision transformer. So Vision Transformer was introduced in about 2021 in a very interesting journal paper, which was basically published by ICLR, and they discussed the entire architecture of Vision Transformer. So these models, of Vision Transformer, they have begun challenging CNNs on like, some of the toughest benchmarks of vision that we have. And slowly and gradually, we're basically redefining that what can be possible for document understanding, medical imaging, and maybe even video classification, right? So now we come to the big question that are vision transformer a natural evolution of deep learning, or they're just a complete revolution in how we will be processing visual data. So let's start with the basics, that what is a convolutional neural network, or like what is CNN? So basically, CNNs were designed for working with image data. So how they operate is that they scan different small regions of an image, and those regions are known as receptive fields. And how do they scan? They scan through filters. Now, what are these filters? Like, what do these filters do? The filters basically, they are pattern detectors. So they're going to scan over the entire image, and they're going to pick up, edges, textures, shapes, any local features available on the image. They're going to pick up those. And layer after layer, CNNs are going to combine all these features to, slowly build a complex and, you can say an abstract understanding of the image. So we can say that, we move from pixels to patterns, and then eventually to an entire object, right? And CNNs have, been powering almost everything. Like, you can see them in image classification. You can also see them in object detection, and even in semantic segmentation. They're still, widely used in the industry. So if I want to give an CNNs will be like as biological inspired artists, like how a painter, when they're building, like when they're painting, they build depth and detail with every new brush stroke. So it's like similarly, CNNs are going to construct an image very incrementally, like they're going to capture finer and broader patterns slowly as they go deeper. Now, the concept of CNN is going to remain incomplete without the understanding of convolution. So, let's break down the core building block of CNNs, which is the convolution operation. Now, if we look at its essence, so, it's just a very simple mathematical operation where we're applying a small matrix, which is called like a kernel or the filter that I mentioned. And it's going to scan across the input matrix here, which is basically a representation of the image. And then this kernel basically convolves, or you can say revolves, or you can say moves around the image. And then on the right, you can see we have an output matrix, which will be storing the results of the operation. So at any position xy, we are basically computing a dot product between the kernel and the corresponding patch in the image. And then, there's output is basically stored. And you can also see how the formula is also given for the convolution operation. Now, quickly, let's go on to the architecture of, CNN. So like here I have like a visual walkthrough of how a CNN will process an image. In this case, we are identifying a car. So like we begin with the input image. Then the input image is basically, passed into the convolution layer. Now, what do convolution layers do is that they basically act like feature detectors. So they're going to scan for patterns like, edges, different corners, different textures, and slowly and gradually they're going to start applying filters to it. Then next we have the pooling layers. Now what do the pooling layers do is that they help reduce the spatial size of the features. Now if I want to put this simply, I would say it's like zooming out. Okay, so you zoom out the image and obviously you lose a bit of detail, but you're also gaining speed and robustness. You're focusing on more important parts of it, right? Then the same process is repeated, for multiple convolution layers and multiple pooling layers. This is and why do we basically repeat the process? So that, we are basically building a network which builds hierarchical knowledge. So, basically from pixels it's going to move towards parts, and then from parts it's going to, move towards the entire object. So what basically happens is that after the pooling layer, it goes towards the fully connected layer. Now, in fully connected layer, we have basically flattened the whole data, and once we pass it through, it's going to give me the output. So it is going to give me the output of the entire image. So, you can say that it's like each layer is building upon the last, and slowly, slowly, we're basically going towards the final understanding of the object. Now coming to the other side, which is a vision transformer. So now vision transformers or ViTs, they are basically representing how now in the recent times you're approaching image processing. So originally the transformer architecture was, for the textual data. It was, a part of natural language processing tasks. But now it is being adapted for visual tasks as well. And that's why we have ViTs have come in place, right? So like CNNs, they scan images pixel by pixel. ViTs divide the image. They divide the image into equal sized patches. And then each of the patches is like, treated like a token. Now, if I explain it in like a textual form, like, we have a word in a sentence, like, each word is a token. Similarly, each patch here is treated as a token. And a very interesting concept, which is like the backbone of Vision Transformer, is the concept of attention. So we apply self attention to understand how each of these patches, are connected to each other, or how do they relate to each other. So, this gives like ViTs a very unique edge. Like, for example, you're not just looking at local texture or edges, but you're actually, looking or capturing a global relationship across the entire image, right? So just like we considered that CNNs are like painters, like, they're adding brush strokes layer by layer. ViTs are strategists, right? So what they do is they map out the entire big picture very holistically. So it's very powerful when we are talking about, understanding the overall context of an image. Like for example, in cases like for example medical scans, now there only a small texture or small feature is not important. The entire scan, understanding of the entire big picture, the entire scan is very important. So in those cases, vision transformer is going to, we preferred. Now, just like we built an understanding of what convolution is, we're also going to take a look at what attention is. So let's look at the core engine which is behind vision transformers, the mechanism of attention. So, it's just as the name suggests, attention is about focus, right? So it basically allows, the model to decide that which parts of the input are more relevant to each other. Or like for example, if I explain it from a human point of view, when we are looking at a visual or when we are looking at a scene, our eyes interpret the important parts of it first, right? So like what we do is that we give more attention, or our main attention goes to the important part of the scene, or the important features of a particular visual that we're seeing, right? Similarly, what we do here through the attention mechanism is that we calculate that which parts of a scene are more important, which deserve more attention. So to do this calculation, we break our input into three components. So we have query, keys, and values. So queries, keys, and values. Now, query is basically what we're looking for. Keys are potential reference points of them, and value is the actual information that we want to retrieve. And then each of these is derived from the input patches. And then basically we use linear transformations, and then scale dot product is used. So and then we calculate scores. Now each of the score is basically telling us that how much attention to pay to a particular patch of the image. So if I put it in very simple term, it's like, how much should I care about this other patch when understanding this one? Basically between two different patches, how much are they related, or how much are they important for each other? Now let's quickly go through the vision transformer architecture. So basically, it's a very different philosophy from CNNs. So what do we do is that first, just like I discussed, that we split the input image into fixed size patches, right? And it's like basically you're dividing the entire image into puzzle pieces, you can say. And each patch is then flattened. We flatten them, and once they're flattened, we pass them through a linear projection, and we turn them into a vector. Now, once I have turned it into a vector, I combine these vector with positional embeddings. Now, what is the concept of positional embeddings? The reason to have a positional embedding is so that we can understand what is the location of each point, right? What is the location of each patch? Because transformers do not understand the order or location without these embeddings. And then everything flows into the transformer architecture, which you can see on the right, transformer encoder, right? This is from the traditional transformer architecture. So all this information then goes into the encoder. And then the block contains, multi-head self-attention layers, which will basically, help each of the patch learn from every other patch. This is why they are going to have that global context, which I mentioned previously. And then after multiple layers of attention and normalization, then we have the final output token. It gets passed to the multi-layer perceptron here, and it makes a prediction, it could classify whether the image is of a car, of a bike, of an animal, whatever. So this is how it works. So if we look at it in a big picture, VITs don't scan locally. They're basically looking at a big picture all at once. So here, this will give you a better idea of how a convolution and attention work in a different manner. So it's basically the same image but with different brains, right? So CNNs will be very good at pattern spotting, and they will be very fast, while VITs will be very good at building relationships between different features, and they're going to work slowly, but they're going to go in the depth. So you can teach CNN faster, but VITs are going to learn the deeper truths that are there. So the analogy here can be seen as maps versus compass. CNNs will follow a path while VITs are going to explore for themselves. Now let's look at what are the core differences. So we're going to have a quick look at each of these. Okay. So now feature extraction. Now when we're talking about feature extraction in CNNs and ViTs, CNNs are like, local pattern detectors. So they will scan small patches of the image, with filters, and they're going to find edges and textures. And, slowly and gradually, as we add more layers, the local information will grow into a global understanding. But when we talk about ViTs are, viewing the image as a sequence of patches. And they basically use self-attention mechanism to learn the relationships between them. So, that gives you basically a better grasp of the bigger picture since the very start. Now, coming to global context, we've already discussed this slightly, but let's have a better look at it. So CNNs will always, build context layer by layer. That's why we have so many layering over there, right? So they start from like local features and then slowly piece together to reach the global structure. But VITs will cut short that process. They like thanks to self attention, they can model any relationships across the entire image in one single layer. That is why it makes them very good for capturing global dependencies. Now, image processing approaches. Now, when we talk about image processing, we just saw that CNN use overlapping filters, right? So that kernel or that filter, it's going to slide across the image, right? So it's going to be, because it's going to be overlapping, so it is, efficient, and it will help in preserving the spatial, structure. But when we talk about VITs, they split images into fixed sized patches, right? And those patches do not overlap. So it's like, how you treat each word in a sentence. These patches will be embedded, and then, they're passed through self attention, and then just like what we discussed. Okay, then moving on to positional encoding. Now, CNNs, they naturally preserve position because, we just saw that they have a grid like convolution operation, right? So since there's a grid, so they know the position is being preserved. But when we talk about VIT or the transformer architecture, they do not have any, way of having the position noted down. So that's why they use the positional encoding. And the concept of positional encoding is that, we inject understand where each patch belongs, like the entire order can be maintained. Then coming to model complexity and data requirements. Now, CNNs are like, they're optimized for image task, right? So they will be very lightweight, and they are going to work well even with smaller data sets. But VITs are heavier, right? They're very computationally extensive, right? So, like self attention will have a lot of computations going on. So it like, VITs normally, want larger data sets so that they can perform well, and, they can avoid overfitting. Okay, then coming to inductive biases. So, CNNs come with very strong inductive biases. Like, they're built to detect those local patterns, be it like edges, be it textures, be it corners. So, it helps them to generalize well. Like, even if the data is limited, they're going to generalize really well. But when we talk about VITs, they're way more flexible. So they don't assume anything about the local structure. But that also means that, they would need a lot more data to learn effectively. Then coming to the point where we discuss their performance on small data sets. So because of, their bias, normally, perform like a lot better when data is limited. While in this scenario, VITs do struggle unless they're pre-trained on, maybe huge data sets, or they have like very strong data augmentation done. So in those cases, they will work well. Otherwise, they struggle to provide good performance on small data sets. So this is just a summarization of all the points that we just discussed. Okay, now it's time for a comparative analysis. So in this section, I'm going to show you a hands-on example where I used a real-world data set to compare the performance of CNN and vision transformers. So I have used the data set of cats and dogs from Kaggle, which contains roughly around 25,000 high-quality, RGB images. So after, I had downloaded the data set, I cleaned and pre-processed the images. So, they were resized, they were labeled, and I splitted them into training and validation sets. And then I also used, the utility functions of data loader of PyTorch. And then finally, let's have a look at the architectures used for CNN and VIT. So, if you have a closer look at the CNN model architecture that I've used, so it starts with three convolution layers, and each of these convolution layers contains we go from 3 to 16, then 32, and then finally, 64. So, it's 3, 16, 32, and then finally 64, right? And we have 64 channels in the end, and each of the convolution block is followed by batch normalization, and we have ReLU activation function, and we have max pooling layers, right? And the reason we have these is so that we can stabilize the training, and we can reduce dimensionality basically. And after the convolution stages, we use basically the fully connected layer. So here I'm using two fully connected layers, and the second layer basically is mapping to two output classes, cats and dogs, right? Okay, so this was the result. So the accuracy came out to be roughly around 75% for CNNs. And then I leveraged the model architecture for vision transformer. Now here we have this with a very different approach. So the input image was resized to 224 by 224 pixels, and then we split it into 32 into 32 patches. So that gives us 49 patches in total, and each of these patch was treated like a token in NLP. And then each of these tokens was projected into a 128 dimension dimensional embedding. And we have a total of 12 layers of the transformer. The depth here, it's telling us that we have 12 transformer layers, and we have 8 attention heads, right, in each layer, which is basically allowing us to capture all the complex relationship between different patches. And after going through the multi-head self-attention and the MLP layer, we finally have two classes which will tell us whether it's a cat or it's a dog. Okay, the accuracy, okay, for this I had 20 epochs, and the accuracy came out to be somewhere around 68 to 69%. So if we basically come to a conclusion of this comparative analysis that we did, so we can say that CNNs are known for their compact size, and how they're efficient with memory usage, and all of this just makes them very ideal for resource constrained environments, right? Because this was run on my own PC without any heavy computational right, where any heavy computational resources available, right? So in contrast, when we come to vision transformers, they excel at capturing all the global dependencies and contextual understanding there is. But however, they obviously require larger model sizes, higher memory requirements, and a lot more data. Now let's have a look at the overall use cases and limitations of these things, like where are CNN still ruling, where vision transformers are shining, and if we have some hybrid architectures. So let's just have a quick look at that. Okay, so despite having the rise of vision transformers, CNNs are still dominating a lot of different areas. Like for example, edge and mobile devices. So CNNs, they're very efficient and compact. So it makes them very perfect for mobile net, efficient net, squeeze net, because these models are being used in smart cameras and different wearables. And then if we talk about real time inference, so CNNs will sometimes process images very quickly, like some even in milliseconds. And this is very crucial when we talk about applications like autonomous vehicles or robotics or AR VR systems. Then similarly, if we talk about small data environments, so in small data environments, CNNs perform really well with fewer training samples. So thanks to their strong inductive biases and simple architectures, this is very much evident in face ID, wildlife monitoring, and real-time lane detection, all of these use cases, like, they are using CNNs widely. But where are VITs shining? So, vision transformers are excelling in areas where, we have very large data sets, or where we have very complex dependencies. Like, when VITs are like, they perform the best when they're pre-trained on, like, data sets like ImageNet 21K, or, like, basically VITs are the best suited for enterprises which have, like, very large amount of data. So, it basically gives state of art results in classification, detection, segmentation, all applications where, you have a lot of data. And in also, again, because, we're using the transformer architecture, so the long range dependencies are also, very well stored, because we have the global architecture, sorry, the global, we have the global self-attention mechanism there. So the VITs are going to be excellent at modeling, the context in medical images, even document OCR tasks and all of these. And then, even for video understanding, when we talk about videos, because, videos are a lot of data, so VITs can basically, very well handle, temporal and spatial features. And they also outperform, 3D CNNs in like benchmarks like kinetics. So, understanding different page layouts in PDFs, all of these applications, they come under VIT. Like, VIT are doing really well in all these applications. Now, there's also been a rise in hybrid architectures, like, getting the best of both worlds. So, like, just I'm going to briefly touch upon two examples. The first one that I have here is ConvNext. Now, this is basically a CNN architecture which was developed by Meta, and it incorporates some of, the transformer principles. So what were the main changes that they did to the architecture was that they replaced batch normalization with layer normalization. Then they changed the activation function, and they performed depth-wise convolutions, with large kernels. So it was, instead of going like, instead of like going horizontally in convolutions, it went vertically, it went in depth. And the impact that came out of it was that connext, it matches or even exceeds vision transformer performance on, like, ImageNet, while also maintaining the speed and efficiency of a CNN. So, like, again, just like I mentioned, best of both worlds. Similarly, we also have Swin transformer. Now, Swin is basically a shifted window transformer that basically, is introducing a hierarchical feature map, which is similar to the CNN architecture, right? So it uses like local attention windows, and it's going to shift for global context. So this, like, here what we're doing is that we're combining the spatial hierarchy of CNNs with like a very flexible attention of vision transformers. So it's like, again, very ideal for, like object detection, segmentation, especially where, we have very high resolution images. And Swin transformers are also being used in Microsoft Azure's image analytics stack. Now, again, a quick look, if like we're using small devices, we're going to prefer CNN. If you're using high resolution medical scans, then, we would prefer VITs, because we would, require the full image context. Then when we talk about surveillance windows, we might go for a hybrid architecture, because in such a scenario, we need the spatial and temporal modeling both, right? Then in real time face unlock, we would prefer CNNs, because, we need it to be very tokens will work better. And if there is very dense segmentation, then we're also going to prefer a hybrid architecture, because, again, best of both worlds. Okay, now coming to the conclusion, we can say that, vision transformers and like CNN, they both offer, like, two distinct approaches to image processing. So, like, while CNNs are excelling at local feature extraction and they're working well with both large and, small data sets, VITs are providing like a very flexible approach that captures the global relationships in images, right? So VITs are typically, performing better on large data sets, but they come with, like, a very high computational cost as well. So Ultimately, it comes down to the choice between CNNs and VITs depending on your task requirement. So basically, you're going to look at what task you have at hand, and then what are your available resources, what are the data set sizes that you have, what are the trade-offs between model complexity, accuracy, performance. And slowly and gradually, as computer vision evolves, we can expect a lot more advancements and a lot more new architectures that will be coming up. So that was all from my side. Thank you so much. Now the floor is open for questions, and feel free to connect with me on LinkedIn. Yes.
Acha, first of all, Assalamu alaikum, ma'am, and thank you. It was a wonderful session. I have a question I wanted to ask. Like, if we want to do feature extraction from a face, say, and we have to like analyze the context in which the person is standing or sitting, or etc. So, should we use CNN or VIT in that case?
Okay, again, it depends on your data set size, right? If you have if you have like a very huge data set, then yes, VITs are going to give you a very good performance on that. But if your data set is small, and let's suppose if you are your fake focus is on their position, whether they're sitting, standing, or their body posture rather than their face, then you can go for VIT. But if you're actually focusing on their facial features, to recognize from their eyes or from their face that let's suppose this picture belongs to person X, so in that case, you're going to prefer using CNNs. So it depends use case upon use case, and what data requirements you have, and how computationally powerful you are.
Okay, ma'am, what I'm trying to do is that I need to analyze the face, but I also need to be aware of the context in which the person is sitting because I am trying to, in a sense, analyze the like the efficiency of a classroom. That's what I'm trying to do. So
All
for
right.
that,
So for that, VITs would give you a better performance. Reason being that they're going to look at the global, the entire global dependencies. So they're going to look at the face as well as the entire big picture, right?
but ma'am, don't you think that in a, for example, real life, if I want to do a real time implementation of this, won't don't you think it's gonna be computationally expensive and won't work as much?
It is going to be computationally expensive, but again, it's always going to be a trade off. So you'll have to decide that where how much accuracy is important to you and how much resources you have. So it's always going to be a trade off, and you'll have to decide for your use case at what trade off sits the best for you.
Okay, so can it be possible that, for example, I currently implement a hybrid approach, and in the future, if I get more resources, I lean more on the uh, VID approach.
I would suggest that you go with a simple architecture first before going into hybrid architectures, because personally, for my own my own project, I implemented a VIT on like a crop data set where I had around 5,000 images, and I was able to do it on a local machine, using Google Colab. I was able to get good results.
Okay, ma'am, thank you.
Any more questions?
So, ma'am,
Yes.
ma'am, it's about the base size. When should be the base size low and when should we the base size should be high? What will be
You're not that audible, you're not that clear. Could you repeat your question?
no? Am I audible now, ma'am?
Yes.
It's about the base size, ma'am. What when should the base size be low and when should be the base size high and would be the impact on the training?
I'm sorry, can you type that question for me because I'm not able to, understand the entire question.
Ma'am, I already typed it in the
Let me
question.
just check. What will be the impact of using a batch size? Okay. So now what is the purpose of, using a batch? Like what is the purpose of the batch size um, in an architecture? It's important to understand that first. So, a batch size in deep learning basically tells you that what will be the number of training examples that will be processed together, in one forward and backward pass through the model, right? So when you are deciding your batch size, you need to decide that instead of feeding the entire data set at once, because you will have memory constraints, so you split it into smaller batches, right? So this will allow you, like the reason why we split it into smaller batches is so that we can allow training on machines to, take place even when we have limited GPU CPU memory, right? So it depends on the resources that you have available, right? You use like a smaller like batch size if you have like, computational power, but like, smaller batches will give you like, they will give you a noisier gradient. That means they will have more variance, right? While larger batches are going to give you more stable and accurate gradient updates, but they might lead to, slower convergence. So your output might convert slower if you're using a large batch size. So it basically depends on, how accurately your model is estimating the gradient during the back propagation, and for that you keep on adjusting your, batch size to smaller or a larger batch size depending on, how your gradient is being estimated.
Okay, ma'am. Thank you.
So smaller batch size is going to give you better generalization but slower training, while larger batch size is going to give you a faster training, but it will need more memory, and it might not be that well in generalizing.